Much with you. Today we are going to talk about counter flow cooling towers. What is the main concept and how can we run our model, and how can we extract our valuable data. Okay, go to your destination folder and double clicking on your model. It's open normally. Anyway, as we demonstrated before from the previous videos, that this is one model for all types of cooling towers. So from the beginning you have to double clicking here, okay, and you have to choose between different types of cooling towers. We demonstrated the cross flow before, so we intended to go through the demonstration of counter flow cooling towers. We have only two types for this one. You have to check this from your menu, and let's go here and little bit emphasize this one, okay, and we have to choose counter flow, hit apply, and okay. We are going to deal with this one, counter flow cooling towers. So this is our specification menu for this one. You have to double click on this one, okay. For cooling towers, counter flow cooling towers, we have, as you can see here, two types. The first one is the circular model, and the second one is conventional cooling tower. I would like to, I do prefer to go through this one as a circular model. I would like to examine it, and it's quite interesting. So I do check this one, okay. Let's go and let's go and assign our valuable inputs in order to examine the performance and the design aspects of this one. Okay, for cooling tower, we have to assign input air temperature, inlet hot water temperature. Okay, suppose it's water temperature at 45 and inlet air temperature at 25. Okay, and let's go for, okay, suppose we need to cool down the amount of 2,500 meter cube per hour with efficiency of cooling tower less than 0.6. okay, suppose it's 0.53. okay, these are our inputs, but beware that for circular mode, circular shape, cylindrical shape, we need to be operated between 600 and 800 ton per hour. Suppose I'm going for the maximum allowable range. It's 800 per unit. This unit is going to cool down 800 ton per hour, meter cube per hour. Okay, that's it. Okay, and going for, this is cross flow, natural air, and counter flow. Let's check here, counter flow. We are dealing with circular mode, not conventional. Okay, that's our model. At this panel, we intended to discover our results. First of all, we have to click save, set your simulation time at 0, and hit run. Let's hit run. It's a fixed point at certain specification. Okay, still in running. Okay, so outlet water temperature is dropped from I think we checked it at 45. It's cooled down to 34, Wood pulp temperature is 25. Outlet air temperature is around 0.35. This is a hot air outlet. Approach is 9. Cooling tower range is 10.6. You can control this by adjusting your temperatures and effectiveness. Sure. And you can get out some important variable parameters such as heat gain, makeup water, blow down losses, total losses, and so on. For design, this is neural network model. It is quite different. This is our fan diameter is 4.2 for 800 meter cube per hour. 4.2 fan diameter. Air mass flow rate is 5.5. And huge amount of mass flow rate. For 5.5 exponential 5 meter cube per hour. And we have here tower weight, tower diameter, because it's a circular. This is diameter of the tower is about 8 meters in diameter. Tower height is 5 meters, and the fan power is around 24.9 to 25, nearly 25 kilowatt of power. Okay, suppose I'm going for dynamic modeling. Set your simulation time at infinity and go out here. We need this panel. That's input panel, submenu, and returning back to our model. I'm sorry, you have to make any change here in order to keep it in surface. Okay, I'm sorry again. I have to. I'm sorry. Let's go here and suppose I'm going from, it's from 6 up to 800. Let's go for 14 meter cube per hour, for example. Okay, and let's return it back here. Okay, it is appeared here, so we can hit apply. Let's go and run our model. Let's hit run. And we keep watching the changes in design parameters here according to the changes in inputs. Let's hit run and keep watching our results. Okay. Yes, you have to increase. Let's go and increasing the flow rate. As you can see here, you realize the changes in design parameters based on the changes in mass flow rate. As you can see here, I'm changing, keep changing, increasing mass flow rate up to, for example, 500 or something like this. Let's go. It needs more faster computer. Anyway, yes, mass flow rate. Okay, increasing up to, for example, up to 800s or 500s. Keep increasing. Okay. And let's go for hot water inlet temperature. I'm going for suppose it's 55. Inlet air temperature, it's around 29, 27, and increasing. Let's go and increase the efficiency, effectiveness of the cooling towers. I'm going to increase up to 1.6.65. It's quite good. Hit OK, and let's go and stop our simulation time. Okay, these are the final values. Okay, so for for counter flow at these final values, I'm going here again, these final values for 55, 27 and for nearly 500 and efficiency 0.66. So we have here, we are going to consume around 6 units of this of 500 in order to cool down 2500 meter cube per day. For data inspector, let's go here. I'm going here. Let's check out our results. Okay, I think this one, because yes, I think this. Let's go down here. I think this is, yes, as you can see, this is your fan power according to the increasing of water mass flow rate. There is increasing of water mass flow rate. So this is the variation of fan power, and this is a tower diameter, and as you can see here, fan diameter. We have here the height, the weight, variation of weight according to your unit. Okay. Number of units decreasing and increasing based on your specifications. Flow velocity through the pipes, condensation, evaporation losses, makeup water, and heat gain by air, heat loss by water, cooling tower range, approach, and so on. Okay, we have here total losses. I think total losses, blew down losses. Okay, and we have here evaporation losses and wet bulb temperature, quite interesting, outlet water temperature. Okay, so suppose I'm going to check another one. Let's go for conventional one. Let's go here. Okay, and we can check this. You have to emphasize a little bit. Okay, and I'm going to check here these parameters, and going here and click on stream selected signals to data inspectors. Okay, and we can for this one we have to double clicking here and click signals. Okay, in order to realize the output on data inspector. Okay, just a few parameters in order to compare between two different models and so on. Okay, saving, but first I have to go here and select another model. For conventional model, it's from 6 up to 300. So I'm going down for, suppose it's 10. I'm sorry. Hit apply. 10 meter cube per hour. Okay. And let's go here for conventional one. I'm sorry, I have to go back again and make some changes. Suppose it's 25. I'm turning back here. Okay, this is another one. Now we are going to check our results. Okay, let's go for here. I'm closing data inspector. Okay, hit apply. Let's hit run. This is conventional one. I've selected it. Let's go and make some our changes according to mass flow rate. And yes, this is mass flow rate. I'm increasing. Let's go and increase and get some new results, and we can roll out our results on the same data inspector results, so we can compare between two different models. I'm going for no more than 300, no more than 300. Okay, that's enough. Let's go and change some operating temperature. I'm going for decreasing, increasing, and just an example about what we are dealing with, or how can we deal with our model. That's cool. Decreasing our temperature. Suppose we are in winter operating conditions. I'm going for 15. Okay, and efficiency, suppose it's decreased down to a specific value, 0.5 or 0.446, 45. That's okay. Now let's hit okay, and let's stop our simulation time. Okay, you have to check data inspector. Let's go and compare our runs between two different models. These data are for the previous one, the circular one. Now we are going to check out our results for this conventional one. I'm going to check. Okay, it needs more faster computer than I expected. Okay, let's go for, suppose I'm going to inspect to compare fan power. Is this your fan? No, is it not this one, fan power? I think so many data. Let's go here. Fan power, it's, I think this one, or this one. Yes, from here. This is the second, the conventional model, and this is the old one, and this is the new one. So you can compare the fan power between two different models. What about the tower diameter? Okay, tower diameter. I think it's tower. Or suppose it's tower weight. Let's go here. No, this one. Or tower height. Yes, tower height. Different in height. Okay. We have here tower weight. Let's go for tower weight. So as you can see here, different between different models. Suppose you are going to extract your data in a figure or something like that, so you can export this. You can export this. Also, you can suppose this is outlet water temperature or evaporation losses, or blow down losses, and you can extract many. This is with bulb temperature. I think yes, with bulb temperature. Yes, it's different in a range of with bulb temperature. Okay, you can send this to a figure. You can click here, send it to a figure, in order to controlling or editing or enhance your figure performance. It will take a little bit time for me because my computer is not faster enough. Anyway, I have to close this one. Enough for data inspector. I'm still waiting. I'm still in wait. Okay, as you can see here, these are your figures, and you can go for properties and opening plot tools. So you can here you can deal with your figures. You can controlling your suppose I'm going to change the color of the curves, or it's tools for your figures, so you can deal with and control. Finally, I would like to thank you for watching. Don't forget to like, share, subscribe. Thank you very much.